Okay, let's unpack this. Today we're doing a deep dive into something pretty fascinating.
Yeah, what have we got?
It's this intersection you might not expect. Advanced math, specifically, differentiation and integration,
Okay.
and agriculture, particularly rotation grazing systems.
Interesting. Calculus on the farm.
Exactly. We've got this excerpt that sort of hints at this connection.
Right.
And our mission, really, is to figure out why. Why would these, seemingly different worlds collide?
And what's the value? I mean, applying these math tools, what could it actually offer?
Yeah, especially if you're maybe, deep in calculus homework right now, or perhaps you're more focused on sustainable farming. This could offer a new perspective.
It's definitely compelling. This idea from the source,
Yeah.
suggesting that concepts we usually think of as purely abstract.
Like rates of change, accumulation.
Exactly. That those could be really powerful tools for understanding and managing something as, well, as complex and dynamic as grazing.
Right. How animals graze, how the land responds over time.
It's not simple.
You really might think calculus for cows.
Hmm.
But rotation grazing isn't static, is it?
Not at all. You've got constant change. Grass growth isn't perfectly linear.
Animal consumption rates fluctuate.
Soil health evolves, with every hoof step, every rest period.
The whole thing is a system just constantly in motion.
And that's precisely where calculus could potentially offer more than, say, just simple averages.
Okay, how so?
Well, differentiation, it's all about the instantaneous rate of change, the speed of something happening right now. So instead of just knowing the, average daily weight gain of an animal over a whole month.
Which is useful, but broad.
Right. Differentiation could maybe help a farmer understand the rate that animal is gaining weight today.
Connecting it perhaps to the specific grass quality in that paddock at this moment.
Exactly. Or maybe the rate grass biomass is increasing in a particular hour under specific sun or rain conditions.
So you're looking at the slope, essentially, the steepness of that growth curve at one precise point, not just the overall change.
You got it. It's about the speed of change.
Okay, so that's differentiation. What about integration?
Well, integration kind of builds on that. If differentiation gives you the rate, integration lets you sum up all that continuous change over a period.
To get a total, an accumulation.
Precisely. Our source implies this could be used to figure out the total forage eaten by a herd over, say, an entire rotation cycle.
Across multiple paddocks, with varying grass availability.
Yes. Or, another example, maybe integrate the rate of soil carbon sequestration.
To understand the total carbon built up in a pasture over a whole growing season.
Yeah. Instead of just the rate carbon is going in right now, you could potentially calculate the total net gain over months.
That really raises a big question, doesn't it?
What's that?
If we can quantify these constantly shifting factors and their cumulative effects using tools like calculus, could that lead to truly optimized decisions on the farm?
You mean predicting the ideal moment to move animals based on projected grass recovery?
Yeah, or determining the absolute best stocking density, maximum production, minimum land damage.
Or even forecasting long-term pasture health based on different grazing intensities. It definitely pushes things forward.
It moves farming beyond just traditional knowledge, important as that is, towards something more data-driven, analytical.
It suggests the biological complexity, the sheer dynamism of grazing, might actually benefit from the kind of sophisticated tools usually found in physics or engineering.
Tools designed for continuous dynamic systems, like differentiation and integration.
Now, our excerpt doesn't lay out specific mathematical models. We should be clear on that.
No, it's more of a suggestion.
But the very idea that these tools are relevant, that points to a potential frontier in agricultural science, doesn't it?
It really does. It challenges us to see math not just as, problems in a textbook,
but as a potential engine for real innovation in critical areas like food production, land stewardship.
So wrapping this up, what does this mean for you listening?
Well, it's a powerful reminder, I think, that the concepts you run into, whether it's in a math lecture or, walking a field,
they can be deeply interconnected.
Yeah, those abstract ideas from calculus might actually hold keys to unlocking more efficient, more sustainable practices right here on the ground.
So to summarize this deep dive, we've explored this really compelling idea from our source.
That the math of differentiation and integration has potential application, specifically within rotation grazing systems.
It really underscores that abstract math can have surprisingly practical uses.
Optimizing complex dynamic systems, like managing land and livestock for, hopefully, better outcomes.
Right. And here's a thought maybe to carry with you from this.
Okay.
Given that constant change, we talked about grass growing, animals moving, soil recovering.
Yeah.
How specifically could focusing on measuring rates of change, that's the differentiation part,
The speed.
or the total accumulated effect over time, the integration part, how could that help a farmer make genuinely smarter decisions?
Think beyond just the simple averages.
Yeah, how might understanding the speed of pasture recovery or the total impact of grazing over a period where things aren't growing linearly, how might that change the game?
Something to ponder.